Hello and welcome back to Decode ISC. In this video, we will be discussing combination circuits. Let's get started. Now think about your phone's calculator for a second. When you press say 1 plus 1, it instantly flashes the answer 2. There is no memory involved here. The calculator doesn't care what you calculated 5 minutes ago. It simply takes your current inputs, processes them, and then gives you your output. This is exactly what a combinational circuit does too. By definition, a combinational circuit is a type of digital circuit whose output at any moment depends only on the input values at the moment. In other words, there is no memory or feedback, and the output is a direct combination of the current input values. Exactly what we saw in the calculator example as well. Let's start with the first combination circuit, the half adder. The half adder is a combination circuit that's used to perform the binary addition of two bits. Let's call them A and B. Now, if you remember from your binary addition class, you remember that when you add two binary units, you'll get a sum and a carry, right? Let's look at the truth table of the binary addition. So say you have 0 and 0, adding them. Your sum is going to be 0, your carry is going to be 0, right? You need to note it like this, 0, 0. If you add 0 and 1, it's going to be 0, 1. So sum is 1, carry is 1. Same thing with 1, 0 as well. Now see, you're adding 1 and 1. What's going to be your answer? 1, 0. So here the sum is 0 and the carry is 1. Now look carefully at this. What does the output represent? The output represents your X or gate, right? Now if you look at this table, what do you see? The output represents the AND truth table, right? So that's very important so that we can write our Boolean expressions. So we can write sum as A XOR B and our carry as A and B, right? Now using this information, we can also construct a logic diagram. A XOR B gives you the sum, while A and B gives you the carry. A half adder is great, but what if you need to add 3 bits? That's when we can look at the full adder. A full adder is also another combinational circuit. Here you add 3 bits where the inputs are A, B, and a carry input called C in. Okay, so look at the truth table here as well. Suppose you're adding 0 plus 0 plus 0, you get 0, 0, right? The sum is 0, the carry is 0. Whatever we've looked at the previous one as well. 0 plus 1 plus 0 is 0, 1. And then 1 plus 0 plus 0 is 0, 1. Again, 1 plus 0 is 1, 0. Sum is 0, carry out is 1. What if it's 1 plus 1 plus 1? Then you have sum and carry, it'll look like 1, 1, right? So sum is going to be 1, carry is also going to be 1, right? Now pay attention to this. What gate is this? This is going to be a little bit more complicated. It's a combination of XOR gate, and this is a combination of AND gate. And also you have to knot it. I'll show you how it looks like. Essentially the sum, I can write the expression as A XOR B XOR C, right? And the carry, I can represent it as A dot B plus B dot C plus C dot A, right? If you look at the logic diagram, it's exactly what it represents. Here X is A, Y is B, Z is C, right? Just change that. So X, A, B, C, XOR gate to give you the sum, and then A, B and it, this is A dot B, this is B dot C, and this is C dot A. And that's how you get your carry, A dot B plus B dot C plus C dot A. This is the logic diagram for a full adder. Now let's move on to the decoder. Now, the decoder is used to convert binary information from n input lines to a maximum of 2 raised to n outputs. Maximum of 2 raised to n outputs. So how many inputs are there? The inputs say are n inputs. So your outputs will denote outputs as m. So this m has to be less than or equal to 2 raised to n. Less than or equal to, because we said the word maximum. Okay, that's what a decoder is used for. Now, the first type of decoder that we're discussing is a 2x4 decoder, right? So again, this is m, this is n. M is going to be less than 2 raised to n. Here, that's 2 raised to 2, right? So that's why m is 4, okay? Now, how many inputs you have? 2 inputs. So x and y, and you have 4 outputs, D0, D1, D2, and D3. Now, how do I construct the truth table for this? Say both x and y is 0, then you're going to write D0 as 1, D1, D2, D3 as 0. Say x is 0, y is 1, then D0 is 0, 1, 0, 0. Then 1, 0 will become, you might guess it by now, this is 1, D2 is 1, 0. If both are 1, this is how it is going to look like. Okay? Now, use this concept and then let's draw the logic diagram for this. If you have to memorize this table, okay? Now, look at the logic diagram. How does it work? So, x, you have an x input line which gives you 1. You're knotting it so that you can get 0 for x. Okay? Same thing you're doing with y as well. So, normal input that gives you 1, knotting it to give you 0 for y. Now, first, in the first line, you have both input as 0. D1 is 1, right? So, for both x and y, I'm going to take from their 0 input line, and then my output is going to be D0. Look at the second line. X is 0, y is 1, and the output is D1. So, x is 0, y is 1, your output is D1. Similarly, we're going to do the same for D2 and D3, and that is how you construct the logic diagram. Now, let's go on to the 3 into 8 decoder. Here, 8 is the number of outputs and 3 is the number of inputs, because output is less than or equal to 2 raised to n, where n is input, here 2 raised to 3, which is 8, and that's how you get m is equal to 8. Right. Now, the application for this is from binary to octal. I told you that a decoder is used to convert binary information. So, you take binary inputs and then you convert it to octals. Now, how do you write your octal numbers? You start with 0, 0, 0, then you go with 0, 0, 1, and you have 0, 1, 0, 0, 1, 1, and so on, right? You remember this? So, that's the same thing you do here, 0, 0, 0, 0, 0, 1, 0, 1, 0, and you write it till 1, 1, 1. You know your binary numbers in octal form as well, right? And the same thing that you did in the previous, this one is, you get your one output in this diagonal manner, right? So, after each input, for each input, the one position shifts. Essentially, it comes in a diagonal manner. This is an easy way to remember your truth table. Okay, how do you construct the logic diagram? Same as what we learned in the 2 into 4 as well. You construct a normal input line for 1. You knot it, use another color, you knot it to get 0. You do that for everything. So, you have 3 inputs here, A, B, C. Here I've denoted that as X, Y, Z. You can denote it as anything. You can use it as A, B, C itself. Let me change that. Right, perfect. And then again, you knot it to give it 0. Same thing that you did in the previous one as well. And then the first line was all of them 0 and the output is D0, right? So, all zeros I'm connecting to give you output as D0, and you do the same thing as you did, similar to what you did in the 2 into 4 decoder. Now we're moving on to the encoder. Now you've understood decoder. Encoder is very simple, because encoder, you can say, is the opposite of what a decoder does. Now, the process of converting from one type to another is what you call an encoding type. Now in decoder, what you did is you converted binary to other types. Here you're going to convert other inputs or any inputs to binary code, right? So the combinational circuit that takes an active signal and converts into binary code. This is the job of an encoder. The first type of encoder that we're going to look at is the decimal to binary encoder. This table simply represents the decimal digits in its binary form. This you probably would have already studied in your Boolean algebra session. If not, just a quick recollection. 0 you can write it as 000. 1 is 0001. 2 is 0010. So on all the way to 9. You can just look at this table. It's simply representing decimal in binary form. Perfect. How do I represent the truth table? The truth table is very simple. You first denote all the input lines from 0 to 9. Now, look at this truth table. A0 is marked 1 at 1, 3, 5, 7 and 9, right? A0 is marked 1 at all these points. Now, wherever it's marked 1, A0, I'm going to draw a line from there. So, at 1 it's marked. From 3 also I'm going to draw a line. From 5, from 7 and 9. Okay. Now, look at, now let's move on to A1, right? A1 is marked 1 for 2, 3, 6 and 7, right? 2, 3, 6 and 7. So when I take my diagram for A1, I'll draw a line from 2, from 3, from 6 and from 7. Similarly, wherever A2 is marked as 1, I will also draw lines from those same points. So here it's 4, 5, 6 and 7. A3, if you look at A3, it's at 8 and 9. So for A3, I'm going to mark from 8 and 9. And that is how you draw this logic diagram. Now we're moving on to the next encoder, the hexadecimal to binary encoder. The hexadecimal to binary encoder. Again, this table is simply representing my hexadecimal numbers in the form of binary code. You will already study this in your Boolean algebra session, right? So 0 is 0000, 1 is 0001 and so on and so forth. How do I draw the logic diagram for this? Same thing again. I denote all my inputs. My inputs are from 0 to 9 and then I go for A, B, C, D, E and F. Then for B0, right? Look at B0. Wherever it's marked as 1, wherever it's marked as 1, I drop a line from there. So here's 1, 3, again, all the odd number 1, 3, 5, 7, 9. And then we have B, D, and F. So then you go here and you draw a line from there. So from 1, I draw a line, I drop a line from 1. Then I drop a line from 3. I drop a line from 5. And then 7, 9. Then B, C, and F, right? That's for B0. Then you can do the same for B1, B2, B3, whatever you've done in the decimal to binary encoder. Same thing, you're going to follow the same pattern, the same logic for the rest of them as well. And that marks the end of this video. Thank you all so much for watching, and I'll see you in the next one. Bye.